topic is range of movement and rotatability. In this topic, we shall discuss the range of movement that a link can perform in a particular linkage, which obviously depends on the relative link lengths. More specifically, the important point in this area is the complete rotatability of a particular link. Now, why this is important? Because as we know, most of the machines are driven by an electric motor, and the shaft of an electric motor is capable of unidirectional complete rotation. So, there must be one link which is connected to this motor shaft should be able to rotate completely, that is, the presence of all other links should not prevent it from undergoing complete or full rotation. This aspect of range of movement and rotatability is most comprehensively studied for 4 link mechanisms, and in this rotatability condition, most important notion is known as Grasshoff's criterion. To start with, let us start with a 4R linkage. That means, there are 4 links which are connected by 4 revolute joints, which we normally call a 4-bar linkage. There are 4 kinematic dimensions in such a 4R linkage, namely which we call the link lengths, that is the distance between successive kinematic pairs. Let us say L min is the shortest link length and L max is the longest link length, whereas L prime and L double prime are the remaining 2 link lengths. Now, Grasshoff's criterion says L min plus L max is less than L prime plus L 2 prime. If the chain satisfies this Grasshoff's criterion, then we call it a Grashoff chain. In a Grashoff chain, the shortest link can always make complete rotation with respect to all other links, whereas the other 3 links, that is except the shortest link, can only oscillate with respect to one another, and this amount of oscillation is always less than 180 degree. So, if in a Grashoff chain the shortest link decides how its kinematic behavior is. In a Grashoff's linkage, we can see 2 crank rocker linkages will be obtained if the shortest link, which is the crank, is adjacent to the frame. That means, a shortest link which has 2 adjacent links. If I make any of this adjacent link as the frame, then the shortest link will be able to make complete rotation with respect to all other links, that means even with respect to the frame. Thus, the shortest link becomes the crank. Because there are 2 adjacent links to the shortest link, it is connected on 2 sides to 2 different links. Any one of these, if I keep fixed or keep it as the frame, then we get 2 crank rockers, because all other links can only oscillate with respect to the frame. If I make a kinematic inversion from a Grashoff chain, we can also get a double rocker linkage if the shortest link is the coupler, that is the link which is opposite to the shortest link, that means which is not directly connected to the shortest link. If I hold that link fixed or use that as the frame, then the coupler, the shortest link, undergoes complete rotation, but the links which are connected to the frame, they can only oscillate. So, we get a double rocker mechanism. If I make another kinematic inversion from the same Grashoff chain, we can get a double crank. A double crank linkage will be obtained if the shortest link is the frame, because all the other 3 links can rotate completely with respect to the shortest link, because it is the relative motion that matters. If the shortest link can make complete rotation with respect to all other links, then all other links can make complete rotation with respect to the shortest link. Now, if the shortest link is held fixed of the frame, then all the other 3 links can make complete rotation. So, we get a double crank. Even the coupler is also capable of making complete rotation. Let us now look at the model of this 4R chain, where the red link is the shortest link, that is L min, and this green link is the longest link, that is L max. Now, if the adjacent link to the shortest link, say this yellow one, is held fixed, and this is a Grashof chain, that is L min plus L max is less than L prime plus L double prime. Now, in this Grashof chain, if I hold one of the links which is adjacent to the shortest link, that is this yellow one, fixed, then we get a crank rocker, because the shortest link is able to make complete rotation with respect to this link, whereas this green link only oscillates with respect to this link. So, we see that the red link is rotating completely, whereas the green link is only performing oscillatory motion, and we get a crank rocker linkage. Another inversion, if I hold this link adjacent to the shortest link held fixed, then also we will get a crank rocker, because this link will also make complete rotation in that case, and this green link will only oscillate with respect to this link. Let us now use the same chain, but with a kinematic inversion. Now, the shortest link is the coupler, and the link opposite to the shortest link, that is this green link, is held fixed. Now, if I move this link, we will see that these two links, which are input and output may be connected to the frame, can perform only oscillatory motion, whereas this coupler is undergoing complete rotation, because the shortest link in a Grashof chain can always make complete rotation with respect to all the other links. Let us see, we start from this horizontal position for the coupler, that is link 3. As we see, it has rotated 90 degree in the clockwise direction. Now, it has rotated 180 degree, it has rotated 270 degree, and it has performed complete rotation. So, from the same Grashof chain, by making a kinematic inversion, earlier we had a crank rocker linkage, and now we had a double rocker linkage. The thing to note is the extreme positions of various links. Why this link number, say this is I call link number 4, this is link number 2, this is link number 3, and this is link number 1, which is the fixed link. Now, let us see why link 4 oscillates. As we see, during this movement, link 2 and 3 have become collinear, and this point cannot go any further. As a result, link 4 now has to return. It cannot go in the clockwise direction anymore, it has to move anti-clockwise direction. So, the link oscillates. Again, in this position, link 2 and link 3 have become collinear, and this is the extreme position of link 4. It has to now rotate clockwise. The same thing is true for link number 2. When link 3 and 4 become collinear, link 2 occupies one of its extreme positions. The other extreme position is again when link 3 and link 4 have become collinear, and link 2 occupies an extreme position. So, we note also this important thing, which will be used later on for displacement analysis, that the extreme position of a link is taken when the two other links become collinear, like this or like this. Let us now look at another kinematic inversion from the same Grashof chain. Here, the red link, that is the shortest link, is held fixed, that is acting as the frame. Now, all these three links can rotate completely with respect to the shortest link. Consequently, we will get what is known as a double crank linkage. That means, all the links connected to the frame, including even the coupler, are able to make complete rotation. So, we see that if it is a Grashof chain, then by kinematic inversions, it is possible to get all the three possible varieties of linkages, namely crank rocker, double rocker, and double crank. two of the inversions resulted in crank rocker when the shortest link is the frame, one inversion when the shortest link is the coupler, we get a double crank, and when the shortest link is the fixed link, we get a double crank. So, we see that if it is a Grashof chain, then by kinematic inversion we can get all the three possible varieties of linkages, namely double crank, crank rocker and double rocker. We get two crank rockers if the shortest link is adjacent to the frame. We get a double rocker when the shortest link is the coupler, and we get a double crank when the shortest link is the frame. So, we have seen that in a Grashof chain, it is the position of the shortest link which decides the characteristics of the linkage, whether it is a crank rocker or double crank or double rocker. Let me now discuss in a non-Grashof chain. In a non-Grashof chain is defined as L min plus L max is greater than L prime plus L 2 prime, where L min is the shortest link length and L max is the longest link length, and the other two link lengths are L prime and L 2 prime. Now, in this non-Grashof chain, whatever may be the inversion, all links can only oscillate with respect to one another. So, in a non-Grashof linkage, all four inversions are double rocker linkages, because all the links can only oscillate with respect to one another. However, the angle of oscillation can be more than 180 degree, whereas in a Grashof chain the angle of oscillation was always less than 180 degree. And also the rockers can cross the line of frame if it is a non-Grashof linkage, whereas in a Grashof linkage one can show that the rocker can never cross the line of frame. If it remains above the line of frame in one configuration, then during the entire movement in a Grashof's double rocker or crank rocker, the rocker can never cross the line of frame. It will be either above the line of frame or below the line of frame. Whereas in a non-Grashof linkage, which is always a double rocker, the rockers can cross the line of frame. That means it can come from above to below or below to above of the line of frame. Now, we explain another thing, that in a non-Grashof linkage there exists only one mode of assembly. The linkage can be driven from one configuration to its mirror image configuration. This needs a further explanation, as we shall do right now. We have just now talked of mode of assembly. Let me explain what do we mean by mode of assembly. For given link lengths, I can have a 4-bar linkage say in this configuration, this O2, A, B and O4. However, with the same link lengths, I could have also assembled this link just in its mirror image configuration, which let me call O2, A prime, B prime, O4. This link length is exactly same as this link length is same as this link length, and this link length is same as this link length. So, O2 AB O4 and O2 A prime B prime O4 are two modes of assembly depending on whether assembled above the line of frame or below the line of frame. It is needless to say that these two configurations are mirror image of each other with the mirror placed along this line of frame, that is O2 O4. Now, if this chain is a Grashof linkage, then we can never drive from one assembly to the other. That means, if I assemble it in this configuration, then by driving this linkage, that is by moving this link, I can never occupy this mirror image configuration. Whereas, in a non-Grashof linkage, if I start from one configuration, then as I drive the linkage, there will be an instant where this mirror image configuration will be taken up by the linkage. These points will be further explained with the help of models. Let us now look at the model of this non-Grashof chain. Here the red link is the longest link, that is L max. This yellow link is the shortest link, that is L min, and these two are L prime and L double prime, the remaining two link lengths. It is easily seen from in this model that L min plus L max is more than the sum of L prime and L double prime. So, it is a non-Grashof chain, and independent of which link we hold fixed, we always get a double rocker linkage. In this particular situation, this longest link, the red link, has been held fixed. So, we see all the links are only performing oscillatory motion, they are unable to make complete rotation. Consequently, we get a double rocker linkage. The thing to note that in this non-Grashof double rocker, these rocking links is crossing the line of frame, that is this line. It is now above. Now, it has crossed, it has gone below the line of frame. So, is true for this rocker, it was above the line of frame. Now, in this configuration, it is below the line of frame. Whereas, in a Grashof double rocker, the rockers could never cross the line of frame, we could never get from above to below. Next, let me demonstrate that the mirror image configuration are taken by the same assembly. Suppose this is the one assembly mode, and we can imagine what will be the mirror assembly mode, that will be like this. Now, if I drive this mechanism, one can see that it has occupied the mirror image configuration. Thus, in a non-Grashof linkage, one can drive the linkage from one mode of assembly to the other, which was not possible in a Grashof linkage. That I will demonstrate with a different model. Now, let us consider another kinematic inversion of the same non-Grashof chain. If we remember, in the previous model, this longest link was the frame. Here, the longest link has been connected to the frame. This is the frame, the fixed link. Here again, even in this inversion, we will get a double rocker linkage. As we see that this is one extreme position of this red link, and these two links have become collinear. And again, this is another extreme position of this red link, when these two links have become collinear. We have also seen that both the rockers could cross the line of frame, and one can easily see that mirror image configuration are taken by the same mechanism. Same assembly can be driven to the mirror image configuration. For this, the mirror image configuration, if we imagine, will be something like this. So, the mechanism could be driven from one mode of assembly to the other, which, as I said earlier, is not possible in a Grashof linkage. Let us now consider another inversion of the same non-Grashof chain. Here, as we see, the longest link, that is this red link, is the coupler. Opposite to this link, that is the frame. Even in this inversion, this is a double rocker. The rocking angle is very large, but still all these links are unable to make complete rotation. The nature of oscillation of these rockers, that is, here as we see, this is crossing the line of frame in this direction, whereas this rocker is crossing the line of frame in this direction. It is not crossing in this direction. So, we see both these rockers are crossing the line of frame in the outward direction, not in this inward direction. Such a rocker is called both outward. Similarly, other inversions from the same chain though had double rockers, but the rocking movements were different, either inward, outward or both inward, and that depends on the position of this longest link. With the longest link as the coupler, we got both outward oscillation, whereas longest link connected to the frame we will get inward outward, and longest link as the frame we will get both inward. So, now we see all the three models from the Grashof chain, non-Grashof chain, sorry, all the three models from the same non-Grashof chain. Link lengths in all these models are equal, only thing the longest link is positioned differently. Here it is frame, here it is coupler, and here it is connected to the frame. And all these inversions has produced, as we have seen, are double rocker linkages. When these two links become collinear, this gets its extreme position. Similarly, when these two links become collinear, this gets its one extreme position. Same is true here. These two links are collinear and this gets its extreme position. So, we have seen different inversion from the same non-Grashof chain always yield double rocker linkages. As a result, such a non-Grashof linkage is not much useful in real life, because if it has to be driven by a motor, then there has to be a crank, whereas no crank exists in a non-Grashof linkage. Thus, only the Grashof linkage is useful in practice if it is to be driven by a motor, and the shortest link must be connected to the motor shaft. Let me now go back to the model of a Grashof linkage and to show that in a Grashof linkage, one mode of assembly cannot be driven to the other mode of assembly, which is the mirror image configuration with the mirror placed at the along the line of frame. For example, this is one mode of assembly. If we dismantle all these revolute joints, I could have assembled it in the mirror image configuration with these two links vertical, but down below this line of frame. But as we see, if we drive this mechanism, this line has become mirror image of its previous configuration, but this link has not, because this is a Grashof linkage, and if it is assembled in one mode, it can never be driven to the other mode of assembly. So, a Grashof linkage has two distinct modes of assembly, whereas a non-Grashof linkage has a single mode of assembly. One more important thing is to see that in a Grashof linkage, it is the position of the shortest link that decides the movement characteristics. Depending on where the shortest link is, it may be a crank rocker, it may be a double rocker, it may be a double crank. Whereas, in a non-Grashof linkage, it is always double rocker, independent of any kinematic inversion. However, it is the position of the longest link that decides the rocking characteristics, whether it will be both inward or both outward or inward outward. Let me now summarize what we have seen so far. In a non-Grashof linkage, we have seen all four inversions are double rocker linkages. The angle of oscillation in a non-Grashof linkage can be more than 180 degree. The rockers can cross the line of frame. There exists only one mode of assembly. The linkage can be driven from one configuration to its mirror image configuration. And lastly, the position of the longest link with respect to the frame decides the type of rocking movement, that is, whether inward outward or outward outward or both outward or both inward or inward and outward. Whereas, for a Grashof linkage, let me go through the similar points. What we have seen for a Grashof linkage, all the three varieties of linkages can be obtained from the same chain by kinematic inversion. Two inversions give crank rocker linkages, which are most useful. One inversion gives a double rocker linkage, and last inversion gives a double crank linkage. However, the angle of oscillation of the rocking links can never be more than 180 degree, it has to be less than 180 degree. Consequently, the rockers of a Grashof linkage can never cross the line of frame. There exist two distinct modes of assembly, that is the two mirror image configuration, and the linkage can never be driven from one configuration to its mirror image configuration. And lastly, it is the position of the shortest link with respect to the frame that decides the type of movement. That is, if the shortest link is frame, then it is a double crank. If the shortest link is the coupler, then it is a double rocker, whereas if the shortest link is connected to the frame, then it is a crank rocker with shortest link as the crank. Now that we are done with both Grashof's and non-Grashof's chain, now let me talk of the boundary between Grashof and non-Grashof, which is known as transition linkage. In the transition linkage, the sum of the longest link and the shortest link is exactly equal to the sum of the remaining two links. That is, L min plus L max is equal to L prime plus L double prime. In general, a transition linkage behaves just like a Grashof's linkage. That is, if the shortest link is the frame, then you get a double crank. If the shortest link is the coupler, then you get a double rocker. If the shortest link is connected to the frame, then you get crank rocker. However, in this transition linkage, when L min plus L max is exactly equal to L prime plus L double prime, then it is obvious that there will be configurations when all the links become collinear. And this collinear configuration is called uncertainty configuration. In these transition linkages, then there are configurations where all links become collinear, which are called uncertainty configurations. Since from these configurations the linkage can move in a non-unique fashion, as we shall demonstrate later with a model. Now, we have discussed in general what happens in a transition linkage, but now we have to discuss special cases of transition chain. As we know, the condition L min plus L max equal to L prime plus L double prime is also satisfied with two pairs of equal links. That means, there are two pairs, one pair of L min and the other pair is L max. Now, in this special case, there are two varieties. Case 1, when the links of equal length are not adjacent, that means, links of equal length are opposite to each other, when we call it a parallelogram chain. In a parallelogram chain, all four inversions are double crank. So, all four inversions of a parallelogram chain yield double crank linkages, of course, with uncertainty configuration, where the parallelogram linkage can flip into anti-parallelogram configuration, as we shall see just now. Let us now look at the model of this transition linkage, that is the special situation of a transition linkage. Here, these two links are of same length, which are opposite to each other, and this coupler length is same as the frame length. That is, we have a pair of L min and a pair of L max. However, because these two equal lengths are not connected directly, they are the opposite sides, it forms a parallelogram and we call it a parallelogram linkage. As this parallelogram linkage moves, it is easy to see that there will be instants where all the four revolute pairs have become collinear. As a result, the linkage is passing through its uncertainty configuration, and from here their non-unique movement is possible. If sufficient care is taken, we can maintain the parallelogram configuration. However, from this uncertainty configuration, it can also flip back to anti-parallelogram configuration, and it is no longer a parallelogram. The two opposite sides are equal, but it is in the crossed configuration. This is called anti-parallelogram. So, at this uncertainty configuration, the linkage becomes uncertain whether to maintain the parallelogram or to flip back into anti-parallelogram configuration. This uncertainty configuration is true for all types of transition linkages whenever L min plus L max is L prime plus L double prime. Again, this is another uncertainty configuration. So, we can either maintain the parallelogram or it can flip back to anti-parallelogram configuration. Thus, to overcome this uncertainty configuration in a parallelogram linkage, we can use an extra coupler, a redundant coupler, which we have seen earlier, and I will show it to you again. Let us again look at this parallelogram linkage where this length is equal to this length and this coupler length is equal to the frame length. So, this is a parallelogram linkage. However, this parallelogram linkage has an redundant or extra coupler which is of same length as this original coupler. As a result, when these 4 revolute pairs become collinear, apparently this parallelogram linkage is passing through uncertainty configuration. However, this extra coupler which is not passing through uncertainty configuration ensures that the parallelogram is always maintained. It can never flip back to anti-parallelogram configuration. The parallelogram linkage is very useful because it maintains unit angular velocity ratio. This crank and the follower are always parallel. So, it transmits unit angular velocity ratio from the input to the output link. But to ensure that it remains a parallelogram and it does not flip back to anti-parallelogram configuration at the uncertainty configuration, we must have this extra or redundant coupler, this one. Let me now summarize what we have just seen for a transition linkage with opposite sides of equal link lengths. Here, as we see, the 4 revolute pairs, namely O2, A, B and O4 have all become collinear. As a result, all the links become collinear, and from this configuration onwards, the linkage moves in a non-unique fashion. If O2A is driven in this direction, O4B can move in this direction or can flip back in the opposite direction. If it moves in the same direction, then it maintains the parallelogram, whereas if it moves in the opposite direction, then it flips into the anti-parallelogram configuration. Here we show that the parallelogram linkage with revolute pair at O2, A, B and O4. What we see that because this is a parallelogram, this angle theta 2 is always same as theta 4 and it maintains unit angular velocity ratio between the input and the output link. However, at the uncertainty configuration A, B prime, O2, O4, everything becomes collinear and it can flip back into this anti-parallelogram configuration. The O2A is still moving in the counterclockwise direction from the uncertainty configuration, whereas O4B has flipped back and moving in the clockwise direction, and theta 2 and theta 4 prime, that is the anti-parallelogram configuration, they are not equal. To maintain the always the parallelogram configuration, that is to avoid this anti-parallelogram configuration after crossing the uncertainty position, we need to have that extra redundant coupler as we explained with the help of a model. Let us now discuss the second case of this special situation of a transition linkage when we have 2 pairs of equal link lengths. However, unlike in a parallelogram situation, here the links of equal length are adjacent, not opposite to each other. And this configuration where the links of equal length are adjacent are called deltoid or kite configuration. Now, from this deltoid or kite configuration, there are 2 different possibilities. We will get a crank rocker if any of the L max, that is any of the longer link is held fixed, and the connected L min will be the crank. Whereas, we get a double crank if any of the L mean that any of the shortest link is held fixed. Such a linkage when we have a double crank is called Galloway linkage. I will explain both this deltoid configuration now with the help of a model. Let us now look at one kinematic inversion from this kite configuration. Here as we see, these two links are of equal link length and these two links is another pair of equal link lengths. Unlike in a parallelogram configuration, here the equal link lengths are adjacent to each other rather than opposite to each other. These two links of equal lengths are adjacent, these two links another pair of equal lengths are adjacent. So, this is the kite configuration. We are considering a kinematic inversion where one of the L max, that is one of the longest link, is held fixed. As a result, we will get a crank rocker with the shorter link which is connected to this fixed link will be the crank and the longer link will be the rocker. As we see, we start from here, the shorter link can rotate completely, whereas the longer link is only oscillating. Here of course, because it is transitional linkage, there will be uncertainty configuration when all the link lengths become collinear. And here you see there is a loss of unique movement, the linkage can move like this, which is no motion transmission, or if care is taken, it can be driven as a linkage with positive motion transmission. So, here we get a crank rocker kinematic inversion with the longer link of this kite configuration held fixed. Next we will see the model from the same chain where one of the shorter link, say this link, will be held fixed. Let us now look at another kinematic inversion from the same kite configuration. Here again two pairs of longer links, one pair of longer links, one pair of shorter links, but one of the shorter link is held fixed. Previously we have seen one of the longer link which was held fixed. In this kinematic inversion, we will get a double crank, that means both this yellow link, the shorter link, and this red link will be able to make complete rotation. As we saw, both the red link and the yellow link were able to perform complete rotation. So, this is a double crank. However, there exists a very fundamental difference between this double crank and the double crank that we got earlier from a Grasshopp's linkage or a parallelogram linkage. There, one rotation of the crank was also causing one full rotation of the follower. But here we must have noticed that it is two revolutions of the shorter crank as we see, the shorter crank has already made one complete revolution, but the longer crank is yet to make its complete revolution. If I rotate the shorter crank one more revolution, then the longer crank is completing its full rotation. Thus, two revolutions of the shorter crank is generating one full revolution of the longer crank. Such a mechanism is called a Galloway mechanism. In fact, we can see that for this configuration of the crank, the shorter crank, with the same link lengths, I could have had another configuration of this linkage. I can draw a circle with this point as center and this as radius, this point as center and this as radius. These two circles can intersect either here or at another point, because two circles normally intersect at 2 points. After one full revolution of this shorter crank, this point is going to the other points of intersection of these two circles, with this point as center and this length as radius, this point as center and this as radius. So, it is quite a different type of double crank than the normal double crank that we have encountered so far, and this has a special name, as I said earlier, is called a Galloway linkage. Another trivial situation of a transition linkage occurs when all the link lengths are equal. That means again L min plus L max is L prime plus L double prime, because all the 4 link lengths are equal. With such equal link lengths, we get what is known as a rhombus linkage. So, in a rhombus linkage, whatever may be the kinematic inversion, just like a parallelogram linkage, we get double crank type linkages, of course, only when the uncertainty configurations are avoided. Here again all the link lengths will become collinear at various configurations, and as we will see, the linkage will move in an uncertain manner at these uncertainty configurations. Let us now look at the model of this rhombus linkage. Here all the link lengths are equal, that is, this length is equal to the coupler length, is equal to the follower length, and also the frame length. All these 4 link lengths are equal, and as a result we get a rhombus. From this rhombus linkage, all 4 kinematic inversions will give you double crank, just like a parallelogram. However, in this rhombus linkage also, as we see, there are uncertainty configurations where all the 4 revolute pairs become collinear, and at these uncertainty configurations the linkage moves in a non-unique fashion. If we maintain the rhombus, it moves with a positive transmission from input to the output, whereas at this uncertainty configuration that linkage moves in an altogether different way. There is no transmission from this link 2 to link 4. Again here we get into uncertainty configuration, and there is no transmission from the input to the output link. However, one can maintain the rhombus and get positive transmission. So, this behavior is very similar to a parallelogram linkage. Now that we have discussed all types of 4R linkages, let us see how can we extend Grasshoff's criteria, that is Grashoff-like criteria, for 3R 1P linkage. Towards this end, let us recall that a curved slider is nothing but a revolute pair. We look at this figure where we have a revolute pair at O2, a revolute pair at A, and a revolute pair at B, and a curved slider between this link 4 and the fixed link, that is link 1. If the center of this circle of this curved slider is at O4, then this linkage is nothing but a 4R linkage with a revolute pair at O2, A, B, and O4. So, we can see the kinematic dimensions. L2 is a link length which is obvious, L3 is a link length which is obvious, and the other 2 link lengths are O4B, which we call L4, and O2 O4, which we call L1. Now, if we come to this 3R 1P linkage, we have a revolute pair at O2, we have a revolute pair at A, and a revolute pair at B, whereas between link 4 and link 1 we have a horizontal prismatic pair. We can imagine this 3R 1P linkage is equivalent to having a revolute pair O4 at infinity in a direction perpendicular to the direction of sliding, which is horizontal. So, now we can think of a 4R linkage O2, A, B, and O4, where O4 is at infinity. Let us look at the kinematic dimensions. Here we have say L2, the link length O2A, and L3, that is the link length AB, whereas the offset, which is this E, that is the perpendicular distance of O2 from the direction of relative sliding passing through B, which is this line. This we call offset which is E. Now, considering O4 at vertical infinity, say in this direction or in this direction, because all vertical lines meet at infinity, then this E, the offset, is turning out to be O2 O4 minus O4B. So, if we call O2 O4 as the L1 and O4B as L4, then this offset is nothing but L1 minus L4. Now, I could have considered this O4 at infinity in the upward direction, that is O4 is at vertical infinity in the upward direction. Then what we see, it is O2 O4 which is L1 and it is this O4B which is L4. I would have got E equal to L4 minus L1. So, for a 3R 1P mechanism, I see there are two lengths, namely L1 and L4, which are infinite. However, the difference of these two infinities, either L1 minus L4 or L4 minus L1, is the other kinematic dimension which we call offset E. So, we can write E as the modulus of L1 minus L4, depending on whether I am considering O4B in the vertically upward direction or vertically downward direction, which will decide whether L4 is more than L1 or L1 is more than L4, and the difference of these two is the offset E. Keeping this in mind, we can decide the Grasshoff's-like criteria. So, we see, as we said, E equal to L4 minus L1. Now, we say the Grasshoff's condition turns out to be the shorter link length L min plus the longest link length, say L4, is less than the other two link lengths, that is L1 plus the other link length, which I for the time being write, say L prime. Now, L4 minus L1 is E. So, this equation I can write L min plus E less than L prime. L4 the infinite length, L1 is the another infinite length, but I have assumed L4 to be more than L1. So, L4 becomes L max. So, L min plus L max less than L1 plus L prime is what we call the equivalent Grasshoff's criteria for a 3R 1P linkage, and that I can convert to L min plus E less than L prime, where E is the amount of offset, L min is the shorter link length and L prime is the other link length. So, if the Grasshoff's condition is satisfied, then the shorter link, that is L min, can make complete rotation with respect to all other links, and we can get a slider crank mechanism. Whereas, if it is a non-Grashoff slider crank, that is L min plus E is greater than the other link length L prime, then no link can make complete rotation and we will unable to get slider crank mechanism, we will get a slider rocker mechanism. So, to conclude in today's lecture, what we have seen, that the rotatability of 4R linkage is most comprehensively summarized by what we call Grasshoff's criterion. When we apply it to a 4R linkage, we seen that L min plus L max less than L prime plus L double prime satisfies the Grasshoff's criteria, and from a Grasshoff's linkage by kinematic inversion we can get all kinds of linkages. Then we have seen the motion characteristics of non-Grashoff linkage, that is when Grasshoff's condition is violated. We have also seen the boundary between Grashoff and non-Grashoff linkage, which we call transition linkages. Then the special cases of transition linkages, where the chain consists of two pair of equal link lengths. At the end, we have also seen how we can modify the Grasshoff's criterion for a 3R 1P linkage, and we got that L min plus E less than L prime. This is the equivalent Grasshoff's condition for a 3R 1P chain, and if this Grasshoff's condition is satisfied, then this shortest link can make complete revolution with respect to all other link, and the shortest link can act as the crank of a slider crank mechanism. Now, I leave the students with a little problem. Can we extend this Grasshopp's criterion for a R, R, P, P type 4R links? There is a link between these two revolute pairs, and there are links between this revolute and prismatic, prismatic and prismatic, and prismatic and revolute. If we recall, we had Scotch-Yoke mechanism of this type, and then elliptic trammel was a mechanism of this type, and Oldham's coupling is a mechanism of this type. In such a linkage, as we see, because there are prismatic pairs, the link between connecting this R and P pair is of infinite length, because the equivalent revolute pair corresponding to this prismatic pair is at infinity. Similarly, this link, which has both prismatic pair at its end, is also of infinite length, and this link connecting P and R pair is also infinite link length. So, there is only one kinematic dimension between these two revolute pairs, let me call that is L2. So, there is one kinematic dimension, that is one link length connecting two revolute pairs, and all other link lengths are of infinite length. Consequently, Grasshopp's condition is always satisfied. As a result, the shortest link L2 will be able to make complete rotation. As we have seen in the Scotch-Yoke mechanism, the crank was always able to rotate completely, or the other two links you find in the elliptic trammel and Oldham coupling, the shortest link was able to make complete rotation with respect to all other links.